Today we're going to discuss a bit more about eigenvalues and eigenvectors. First, let's review some concepts that we had from our last lesson. Let's say that T is a linear transformation. We'll say that T is diagonalizable if there exists an ordered basis beta such that the matrix representation, square bracket T from beta to beta, is a diagonal matrix. That is, we can write this matrix representation as that n by n matrix that consists of these scalars, lambda 1, lambda 2, through lambda sub n that appear along the diagonal. This is equivalent to saying that there exists vectors v sub j such that t applied to v sub j is a scalar multiple of v sub j. We'll say that a squared matrix A is diagonalizable if the linear transformation left multiplication by A is diagonalizable. To be more precise, what we mean is follows. Let's say that gamma is the standard basis for the n-dimensional vector space F to the n. Then we know that the matrix representation of the left multiplication by A transformation with respect to the basis gamma is just our n by n matrix A. For any other basis beta, we then have a change of coordinate matrix Q. Now, the matrix Q inverse times A times Q should be the matrix representation for left multiplication by A with respect to the basis beta. We would like for this matrix representation to be the same diagonal matrix that we saw above. We'll continue with more definitions here. Again, say that T is a linear transformation from a vector space V to itself. A non-zero vector lowercase v is called an eigenvector if there exists a scalar such that T applied to lowercase v is the scalar lambda times r lowercase v. The scalar lambda is called the eigenvalue associated to the eigenvector lowercase v. Now say that A is an n by n matrix. We'll say that a non-zero vector x is an eigenvector for A if there exists a scalar lambda such that A times x is lambda times x. Similar to above, the scalar lambda is called the eigenvalue associated to the eigenvector x. For the next several lectures, we're going to be concerned with how to compute such eigenvectors lowercase v and eigenvalues lambda for either linear transformations T or matrices A. You may want to keep the following diagonalization problem in mind. First, does there exist an ordered basis beta for our vector space V such that the matrix representation square bracket B with respect to beta is a diagonal matrix? Second, if such a basis beta exists, how can it be found? Let's review an example that we discussed last time to get some better intuition behind what eigenvectors and eigenvalues are. Let's consider the real plane R2. For any real number m, we consider the following linear transformation that you see on your screen. Simply put, this is the reflection about the line defined by y equals mx. For example, when m is equal to 0, this linear transformation takes a vector x comma y to the vector x comma negative y, which is simply a reflection about the x-axis, namely the line y equals 0. We then can consider the standard basis consisting of the vectors e1 and e2, but it'll be a little bit better if we consider a slightly different basis consisting of the vectors v1 and v2 that you see here on your screen. Intuitively, v1 is the direction of the line y equals mx, whereas v2 is the direction of the line perpendicular to the original line. Then t applied to v1, you can check, it's just positive v1, whereas t applied to v2 is negative v2. This is exactly the definition of a reflection. If we have a direction v1 along the line y equals mx, we can reflect and get back another point on the line with no changes. However, if we're perpendicular to the line, say if we have a vector v1 that perhaps is pointing up, its reflection should be negative v2, which now points down. Again, it's easy to see that v1 is the span The span of V1 is our line L, whereas the span of V2 is our line L perp, which corresponds to y equals negative 1 over m times x. But we want to keep in mind that with respect to the basis beta, consisting of V1 and V2, we then have this matrix representation, square bracket T from beta to beta, which is a diagonal matrix in the form 1, 0, 0, minus 1. This actually means that both T and our matrix A are diagonalizable. Today we're going to continue with some main properties of eigenvalues and eigenvectors. The goal for today is to explain how to compute eigenvalues of a given linear transformation T. Let's say that V is a finite dimensional vector space with a basis beta. We'll assume that T is a linear transformation from V to V, and let's denote A as the matrix representation of T with respect to this basis beta. First, T is diagonalizable if and only if there exists an ordered basis beta consisting of eigenvectors of T. Further, if T is diagonalizable, then the matrix representation with respect to beta is a diagonal matrix. And the entries in this diagonal matrix are simply the eigenvalues associated to the eigenvectors in our ordered basis. Second, the following four statements are equivalent for any scalar lambda. Lambda is an eigenvalue for the linear transformation T. Lambda is an eigenvalue for the matrix representation A. The determinant of A minus lambda times the identity matrix is 0. And there exists a non-zero vector, lowercase v, such that lowercase v is in the null space of the linear transformation T minus lambda iv. Finally, for any variable t, the n by n determinant, what we're defining as f of t, which is the determinant of A minus t times the n by n identity matrix, is a polynomial of degree n, which is independent of the choice of basis beta. In particular, our linear transformation T has at most n distinct eigenvalues lambda. We're going to spend some time proving this theorem, but first let's explain how to use this result to compute the eigenvalues lambda of a given linear transformation T. First step, we'll choose a basis beta of our vector space V. Doesn't matter which basis we choose. Second, we'll compute the n by n matrix A, which is just the matrix representation of T with respect to this basis beta. Third, we'll compute the degree n polynomial f of t, which is the determinant of the matrix A minus t times I sub n. Next, we'll compute the roots lambda of the equation f of lambda equals 0. These roots are the desired eigenvalues of our linear transformation T. You'll see that this polynomial f of t is rather important. We call f of t the characteristic polynomial of our linear transformation capital T. You may wish to compare all of these properties with some exercises from the textbook, but let me point out now that we'll see later how to compute the eigenvectors of our linear transformation. This algorithm just explains how to compute the eigenvalues lambda for the moment. Now, we'll sketch over the proof of the theorem. Again, this is rather long, but we'll just sketch over the main ideas. First, let's skim over how to prove the first statement. Let's assume that T is diagonalizable. Then this means that there exists an ordered basis beta, such that our matrix representation is a diagonal matrix, so let's let lambda j just be the diagonal entries. We know from the way that we set up our matrix representation that T of Vj is lambda j times V. We now need to really prove that the V sub j's are eigenvectors. That actually means that the V sub j should be non-zero. Well, if the V sub j's were 0, then this would be a contradiction because 0 cannot be an element of the basis because our basis, of course, is a linearly independent set. Conversely, let's say that we do have an ordered basis consisting of eigenvectors. Then it's simply a matter of realizing that T of Vj is lambda j times Vj, so that our matrix representation is indeed a diagonal matrix. Now let's prove the second statement. We have a series of 4 equivalent statements that we need to show. First, let's set some notation. Recall that the standard representation, phi sub beta, takes a vector lowercase v from our vector space capital V, and it returns the coordinate vector square bracket v. That is, if lowercase v is a linear combination a sub 1 times v1 plus a sub 2 times v2 plus a sub n times vn, then our standard representation, phi sub beta v, is just the n-dimensional vector consisting of the scalars, a sub 1, a sub 2, through a sub n. Moreover, let's let lambda be any scalar. It doesn't have to be an eigenvalue for the moment. We'll denote capital B as the matrix A minus lambda times I sub n, and we'll denote L sub B as the left multiplication by this matrix B. Let's show that 1 implies 2. We'll assume that this lambda is an eigenvalue for our linear transformation T. Since phi sub beta, our standard representation, is 1 to 1, and we know that phi sub beta sends the 0 vector to the 0 vector, then we'll see that our standard representation of the vector lowercase v is a non-zero vector as well. But now a times x, where x is this coordinate vector for our vector lowercase v, is just lambda times x. Hence, lambda is an eigenvalue for our matrix A. Next, let's assume that lambda is an eigenvalue for our matrix A. Then A times x is lambda x, so that LB, left multiplication by our matrix B, of x is just the 0 vector. That means that there is an element in the null space of left multiplication by our matrix B. But then this shows that the rank of this left multiplication is strictly less than n, so the determinant of B must be 0, but because B is A minus lambda times the identity matrix, we see that the determinant of A minus lambda in must be 0. Now let's show 3 implies 4. Let's assume that this determinant is 0. Then, of course, B must not be an invertible matrix, but then this implies that the rank of left multiplication by B is strictly less than n, but this implies that there must be a non-zero element in the null space. Let's denote this non-zero element as x. Then, if we take a look at how x corresponds via the standard representation to some vector lowercase v in our vector space capital V, we actually see that lowercase v must be an eigenvector. But the more important statement is that lowercase v must lie in the null space of the linear transformation T minus lambda IV. Finally, let's assume that there's a non-zero vector, lowercase v, that exists in the null space of the linear transformation T minus lambda IV. As mentioned before, this is really the same thing as saying that lowercase v is an eigenvector of the transformation T. But because v is an eigenvector, we do see from this equation that lambda is the associated eigenvalue. Finally, we'll show the third statement. We're going to do so in several steps. First, let's take a look at this determinant, which we call f of t. We're going to show that this is independent of the choice of basis beta. Well, if beta prime is another basis, we can consider the change of coordinate matrix Q. What we'll find is that Q times our new matrix A prime, which is the matrix representation with respect to the new basis beta prime, Q times A prime minus TIN must equal A minus TIN times Q. So upon taking the determinant of both sides, we see that the determinant of A prime minus TIN is the determinant of A minus TIN for any basis beta prime. So indeed, f of t must be independent of the choice of basis beta. Next, let's show that this f of t is really a polynomial of degree at most n. We'll prove this by induction. Actually, we're going to prove a stronger statement. let's say that A and B are two n by n matrices. Then the determinant of A plus t times B is a polynomial of degree at most n. Well, when n is equal to 1, this is the base case. This is rather easy because the determinant is just simply a linear polynomial, a11 minus t times b11. So let's assume the inductive hypothesis. That is that this statement, p of n, is true when n equals some integer n0. We'll now perform the inductive step by looking at polynomials of size n0 plus 1. Visually, our matrices look like this. A plus t times b will be the matrix that you see here on your screen. We can now consider the n0 by n0 matrix found by deleting row I and column j. This, of course, is given by aij tilde plus t times bij tilde. By looking at the definition of the determinant and expanding along row I, we then see that the determinant of a plus t times b is a sum of a linear polynomial, a in 0 plus 1j plus t in 0 plus 1j, times the determinant of a smaller n0 by n0 matrix. However, by the inductive hypothesis, the determinant of this n0 by n0 matrix involving the tildes is a polynomial of degrees at most n0. But if we have a polynomial of degree n0 times a linear polynomial, then we see that we have a polynomial of degree at most n0 plus 1. Hence, proposition P of n must be true. Finally, we show that our polynomial f of n must be in the form that you see here, that it has a constant term, which is determinant of a, plus all the way through a leading term, t to the n, that has some coefficient, -1 to the n. For our previous result, we know that our f of n must be a polynomial of degree at most n. Setting t is equal to 0, we do see that the constant term, a0, is the determinant of a. Now, we want to be a little bit careful to try to figure out what is the leading term. Why is it -1 to the n? Well, we can simply reverse things to take a look at the determinant of k times a minus I sub n. Now, we can set this k is equal to 0, and we find that the leading term, a sub n, is just the determinant of negative the identity matrix. But negative the identity matrix just looks like a diagonal matrix with -1s along the diagonal. And we found before that the determinant of a diagonal matrix is just the product along the diagonal entries. Hence, the leading term, a sub n, must be -1 to the n. Finally, we're going to show that n is the largest number of distinct eigenvalues for a linear transformation, T. For the moment, let's say that T has m eigenvalues, lambda1, lambda2 through lambda sub m. And of course, as before, we'll let f of t denote this polynomial of degree n. And let's denote g of t as the following polynomial of degree m, where we have the root of g of t to be the eigenvalues lambda1 through lambda sub m. Using the division algorithms, we know that we can find polynomials q of t and the remainder r of t, since that f of t is q times g plus r. And of course, the degree of r should be strictly less than the degree of g. Next, we know that the eigenvalues lambda sub j of t must be roots of f of t. So plugging things in, we see that r of lambda j must be 0 as well. However, r of t has degree at most n, m, and we know that r of t has at least m roots. So this means that r of t must be the constant polynomial, namely 0. Hence, f of t must be q of t times g of t. But now this shows that n is greater than or equal to m, hence showing that there are at most m distinct eigenvalues. So this completes the proof of our theorem. Thanks very much for watching.